Hey everyone, welcome back to Simple Understanding channel. If you're preparing for the APICS Certified Supply Chain Professional Exam or planning to start soon, you're in the right place. This video is part of our CSCP learning playlist, where we break down complex topics into clear, practical lessons. Today, we're focusing on something that often challenges many test takers: quantitative and analytical problem solving. We'll go step by step through 10 realistic CSCP-level math problems, each one carefully designed to mirror the actual exam in logic, style, and difficulty. You'll learn how to interpret each question, how to think strategically like a supply chain professional, and how to reach the correct answer with confidence. And remember, this video is just one part of the complete CSCP study materials bundle that I've built to help you master the entire exam, not just the math section. Inside the bundle, you'll find concise notes, visual summaries, concept maps, question banks, mock exams, and step-by-step problem-solving videos. Everything you need to understand, practice, and pass the CSCP exam. You'll find the download link in the description below, along with a full CSCP playlist, so you can study module by module at your own pace. So grab your notebook, pause when you need to, and solve along with me. Let's get started. Here are your top 10 CSCP math problems, explained in the clearest and most practical way possible. Problem 1. Forecast accuracy. A supply planner wants to check how accurate their demand forecast has been for a particular product. Over the past 4 months, the actual customer demand was 1,200 units, 1,400 units, 1,100 units, and 1,300 units. During those same months, the forecasted demand was 1,250, 1,350, 1,000, and 1,200 units. The planner wants to know, on average, how far off the forecast were in percentage terms. In other words, the product's mean absolute percentage error. Problem 1. Forecast accuracy. MAPE problem. A planner wants to evaluate forecast accuracy. The actual demand for 4 months was 1,200, 1,400, 1,100, and 1,300 units. The forecasts were 1,250, 1,350, 1,000, and 1,200 units. We need to find the mean absolute percentage error, or MAPE. Explanation. Problem 1. Let's check how accurate the forecast really was. For each month, we compare the forecast with the actual demand to find the error, whether the forecast was too high or too low. Next, we take the absolute difference because we only care about the size of the error, not its direction. Then, we divide each absolute error by the actual demand to find the percentage error for that month. Finally, we take the average of those percentages. After running the numbers, we find that the average forecast error, or MAPE, is about 6.6%. That means, on average, the forecasts were off by roughly 7%, a fairly reasonable accuracy for short-term planning. Problem 2. Economic order quantity. A distributor sells 24,000 units of a product each year. Every time the company places an order with its supplier, it costs $60 to process that order. In addition, keeping items in inventory costs about $4 per unit for the year. The goal is to find the most economical order size, the quantity that keeps both ordering and carrying costs as low as possible, and to calculate the total yearly cost at that level. Problem 2. Economic order quantity, EOQ. A distributor sells 24,000 units per year. Each order costs $60 to place, and the annual carrying cost is $4 per unit. We need to find the most economical order size and the total yearly cost of ordering and holding inventory. Explanation. Problem 2. This is a classic EOQ question. First, we balance two opposite costs, ordering costs and carrying costs. Ordering costs go down when we place larger, less frequent orders, while carrying costs go up because we hold more inventory. The economic order quantity is the point where these two costs are equal. After calculating, we find that the best order size is about 850 units. At that level, the total annual cost, combining ordering and holding, is around $3,400 per year. That's the sweet spot that minimizes total cost. Problem 3. Safety stock for a target service level. A manufacturer wants to protect against unexpected changes in customer demand. On average, the company sells 400 units of a certain component each week, and the weekly demand typically varies by about 50 units up or down. It usually takes 2 weeks from the time an order is placed until new stock arrives. The company wants to meet customer demand 95% of the time without running out of stock. How many extra units should be kept in safety stock to reach that level of service? Problem 3. Safety stock for a target service level. Average weekly demand is 400 units, and the standard deviation is 50. Lead time is 2 weeks, and the company wants a 95% service level, corresponding to a Z-value of 1.65. We need to calculate the safety stock. Explanation. Problem 3. Safety stock protects us against demand variability during lead time. First, we measure the variation in demand over the lead time period. Because lead time is 2 weeks, we multiply the weekly variation by the square root of 2 to find the combined variation. Next, we multiply that by the service level factor, which is 1.65 for 95% confidence. That gives us about 117 units of safety stock. So, by keeping around 120 extra units on hand, the company can meet 95% of customer demand without running out. Problem 4. Reorder point. A factory uses about 60 units of material each day. It takes 8 days from the time a new order is placed until that material is delivered. The factory also wants to keep 100 extra units on hand as safety stock to protect against possible delays or demand spikes. At what inventory level should the company place its next order so that it doesn't run out before new stock arrives? Problem 4. Reorder point, ROP. Average daily demand is 60 units. Lead time is 8 days, and the company keeps 100 units of safety stock. We need to find the reorder point. Explanation. Problem 4. The reorder point tells us when to place the next order so that new stock arrives just as the old stock runs low. We start by multiplying daily demand by the lead time. That's 60 units per day for 8 days, or 480 units. Then we add the safety stock of 100 units. That gives us a total reorder point of 580 units. So when inventory drops to 580, it's time to reorder. Problem 5. Capacity utilization. A production plant can make up to 10,000 units per week when running at full capacity. However, on average, it actually produces about 8,500 units each week. We want to find the plant's capacity utilization rate and discuss what that number says about how efficiently the plant is operating. Problem 5. Capacity utilization. A plant has a weekly capacity of 10,000 units, but currently produces 8,500. We need to find the utilization rate. Explanation. Problem 5. Capacity utilization shows how much of the available capacity is actually being used. We divide actual output by the total capacity and convert it to a percentage. 8,500 divided by 10,000 equals 85%. That means the factory is running at 85% of its potential. Healthy performance, but with some room to grow. Problem 6. Inventory turnover and days of supply. A company records an annual cost of goods sold of $4,800,000. Throughout the year, the company's inventory value averages about $600,000. We need to determine how many times the company sells and replaces its entire inventory in a year, known as the inventory turnover, and how many days of supply that represents. Problem 6. Inventory turnover and days of supply. A company's cost of goods sold is $4,800,000, and its average inventory is $600,000. We need to find the inventory turnover ratio and the average days of supply. Explanation. Problem 6. Inventory turnover tells us how often inventory is sold or used up each year. We divide the cost of goods sold by the average inventory value. 4.8 million divided by 600,000 gives us 8 turns per year. To convert that to days of supply, we divide 365 by 8, giving about 46 days. So, on average, the company holds roughly a month and a half of inventory before it's sold or replaced. Problem 7. Total landed cost comparison. A buyer needs to choose between two suppliers that offer different prices and shipping costs. Supplier A charges $20 for each unit and adds a freight charge of $2,000 for every shipment of 1,000 units. Supplier B charges a slightly lower price of $19 per unit, but a higher freight charge of $3,500 for the same shipment size. Which supplier actually offers the lower cost per unit once shipping is included, and by how much? Problem 7. Total landed cost comparison. Two suppliers offer different prices and freight costs. Supplier A charges $20 per unit plus $2,000 shipping for every 1,000 units. Supplier B charges $19 per unit but $3,500 shipping for the same volume. We must determine which supplier has the lower landed cost per unit. Explanation. Problem 7. Let's look beyond just the purchase price. Supplier A's total per unit cost includes both the unit price and the shipping spread over 1,000 units. That's $20 plus $2 freight, or $22 per unit. Supplier B's cost is $19 plus $3.50 freight, which totals $22.50 per unit. So supplier A is cheaper by 50 cents per unit. Even though supplier B offers a lower unit price, the higher freight cost makes it less economical overall. Problem 8. Cycle time improvement impact. A production line currently produces 500 finished units per day. Each unit takes about 1.2 minutes to make from start to finish. The company plans to improve the process, reducing the time required to make each unit by 15%, while keeping the same number of work hours in the day. How many additional units will the line be able to produce each day after the improvement takes effect? Problem 8. Cycle time reduction impact. A line currently produces 500 units per day with a cycle time of 1.2 minutes per unit. If process improvements reduce the cycle time by 15%, how many additional units can be produced per day? Explanation. Problem 8. Cycle time is how long it takes to produce one unit. First, let's find how much total time is available in the day. At 500 units per day and 1.2 minutes each, that's 600 minutes of production time. If the new cycle time is 15% shorter, it becomes about 1.02 minutes per unit. Now, divide the same 600 minutes by the new time per unit, and we get roughly 588 units. That means the plant can make about 88 more units per day after the improvement. Problem 9. Cash-to-cash cycle time. A company wants to understand how long its money is tied up in operations. It typically keeps 40 days' worth of inventory on hand, waits about 30 days to collect payment from customers, and takes 25 days on average to pay its suppliers. Based on these figures, how long is the company's cash-to-cash cycle? The period between paying out cash and getting it back? Problem 9. Cash-to-cash cycle time. A firm reports 40 days of inventory, 30 days of receivables, and 25 days of payables. We need to determine the cash-to-cash cycle time. Explanation. Problem 9. The cash-to-cash cycle measures how long a company's money is tied up in operations. We add the days of inventory and the days of receivables, then subtract the days of payables. So, 40 plus 30 minus 25 equals 45 days. This means it takes about 45 days from paying suppliers until the company collects cash from customers. The shorter that number, the healthier the cash flow. Problem 10. Distribution network optimization. A retailer currently operates one distribution center that costs $300,000 per year for transportation and $100,000 per year for facility operations. Management is considering opening a second distribution center. If they do, transportation costs would fall to $220,000 per year, but total facility costs would rise to $180,000 per year. Should the retailer go ahead with the expansion, and how would the total annual cost change as a result? Problem 10. Distribution network optimization. A retailer currently operates one distribution center with transportation costs of $300,000 and facility costs of $100,000 per year. If the company adds a second distribution center, transportation cost drops to $220,000, but total facility cost rises to $180,000. Should the retailer expand? Explanation. Problem 10. Here we compare the total cost before and after the change. Currently, transportation plus facility cost equals $400,000. With a second distribution center, transportation goes down, but facility cost goes up, still totaling about $400,000. So, from a cost perspective, there's no financial gain. However, the decision might still make sense if the second center improves service levels, delivery speed, or risk resilience. And that's it. Those are the top 10 realistic CSCP-level math problems, explained step by step. If you found this helpful, make sure to hit like, subscribe, and turn on the notification bell so you won't miss the next lessons in this CSCP series. Remember, this video is part of the full CSCP exam preparation playlist, which covers every module from forecasting and sourcing to optimization and risk management. You can find a playlist link and a download link for all CSCP study materials right below in the description. Thanks for watching Simple Understanding, where we make supply chain concepts simple, practical, and exam ready. I'll see you in the next video.